Welcome everyone. Today we are going to solve a very interesting problem in projectile motion. We have two projectiles thrown at different angles, but they travel the same horizontal distance. Their initial speeds are also the same. What we are given is their individual times of flight, and from just that information, we will calculate the range. Let us begin. Let us read the problem carefully. We have two projectiles, and both are launched with the same initial speed. They also cover exactly the same horizontal distance, meaning their ranges are equal. However, they are thrown at different angles and they spend different amounts of time in the air. The first projectile is in the air for 10 seconds and the second one for 5 seconds. Our goal is to find this common range. Before we start solving, let us recall the two most important formulas in this problem. First, the range formula, r equals u squared times sine of 2 theta, divided by g. Second, the time of flight formula, t equals 2u sine theta divided by g. Now here is the most important insight. If two projectiles have the same initial speed and the same range, then their angles must add up to 90 degrees. This means θ1 plus θ2 equals 90. We will use this fact as the foundation of our solution. Step 1. Since both projectiles have the same range with the same initial speed, the range formula tells us that sine of 2 θ1 equals sine of 2 θ2. This leads to 2 θ1 plus 2 θ2 equals 180 degrees. Simplifying, θ1 plus θ2 equals 90 degrees. This means sine of θ2 equals cosine of θ1. Step 2. We write the time of flight for each projectile separately. T1 equals 2u sine θ1 over g, which is 10 seconds. T2 equals 2u sine θ2 over g, which is 5 seconds. Now we multiply these two equations together. This gives us T1 times T2 equals for u squared times sine θ1 times sine θ2, all divided by g squared. This multiplication is the clever trick that makes everything simplify beautifully. Step 3. We now substitute sine θ2 equals cosine θ1 into the product we found. T1 times T2 becomes for u squared times sine θ1 times cosine θ1, all divided by g squared. Using the double angle identity, this equals 2u squared times sine of 2 θ1, divided by g squared. Now, from the range formula, we know that u squared times sine of 2 θ1 equals a times g. Substituting that in, T1 times T2 equals 2rg divided by g squared, which simplifies to 2r over g. Rearranging, we get r equals g times T1 times T2, divided by 2. Step 4. Now we simply plug in the values. G is 10, T1 is 10, and T2 is 5. So R equals 10 times 10 times 5 divided by 2, which equals 500 divided by 2, which equals 250 meters. Let us summarize what we have done. The master formula we derived is R equals G times T1 times T2, divided by 2. This is an elegant result that directly connects the range to the two times of flight. Step 1 used the condition of equal ranges to establish that the angles are complementary. Step 2 multiplied the time of flight equations to set up a useful algebraic expression. Step 3 used the complementary angle identity and the range formula to simplify everything. Step 4 was simple substitution to get 250 meters. Remember this master formula, it is very useful whenever two projectiles with the same speed have the same range. And there we have it. The range is 250 meters, which corresponds to option 1. The key takeaway from this problem is the master formula, R equals G times T1 times T2 divided by 2. This beautifully shows that once you know the two times of flight, you do not need to know the individual projection angles at all. The physics does all the work for you through the complementary angle relationship. I encourage you to practice similar problems by changing the values of T1 and T2 to build your confidence. Thank you.